All right. So, as I said, we're going to be doing 8.3, which is improving performance of the Rankine cycle, which is superheat, reheat, and supercritical. So these are all ways that we can try and get more out of what we had, right? In the previous example that we did in class, they only heated up the steam to saturated vapor, right? Only saturated vapor. But you can actually get more out of it if you heat this up more, right? You can get more work out. Obviously, you'll have to put more energy in to get it all the way up to where you want it to be, like up here in the superheated region. But the point is that we're trying to get more out, right? So let's go back down and get back to this. So it says, the representations of the vapor power cycle considered thus far do not depict actual vapor power plants faithfully, for various modifications are usually incorporated to improve overall performance. In this section, we consider cycle modifications known as superheat and reheat. Both features are normally incorporated into vapor power plants. We also consider supercritical steam generation. So, superheat and reheat. Essentially, what superheat is that the power plant goes to the superheated region, right, before it goes into the turbine. And reheat is after the turbine, instead of going to a condenser, it goes back to the boiler and runs through the turbine again, and then it goes to a condenser, right? Or it does that a couple of times. It might have a couple of reheats. But essentially, you're getting heat. You're getting your heat generated is also heating up. It's heating up more than one thing. It's not just heating up the very first state of steam from 1 to 4. It's heating it up again and then again and again, so you can get more power, right? So let's talk about this. It says, let us begin by discussion by noting that an increase in the boiler pressure or a decrease in the condenser pressure may result in a reduction of the steam quality at the exit of the turbine. This can be seen by comparing states 2 and 2 prime and 2 double prime of figures 8.4 and 8.4b. We'll look at that in a second, to the corresponding state 2 of each diagram. If the quality of the mixture passing through the turbine becomes too low, the impact of the liquid droplets in the liquid-vapor mixture can erode the turbine blades, causing a decrease in turbine efficiency and an increased need for maintenance. So what it is saying is that if we have, which I'll pull this up, Epic Pen, sorry. If we have a saturated vapor going in, so we're going to draw our TS diagram here, right, as we did before. I know this is like a kind of a bad drawing. I'll actually try this again. So if we have state 1, which you guys recall is the turbine inlet, right? So turbine inlet is right here. And let's say down here is turbine exit at state 2, right? Somewhere over here. State 2. Nope, that can't be how it is, sorry. I can't go backward an inch, my fault. Bad drawings. So we'll just go down to this right here. So if this is 2, in between here, the turbine 1 to 2 is the turbine stage, right? And so what they're saying is that if in between here we have too much liquid, because right here you guys can clearly see that during the middle of this from 1 to 2, there will be liquid inside the turbine, right? Because our quality is no longer 1. This is start at saturated vapor. It has to end at some quality of maybe like 60-70%. So there is a liquid in the turbine. And if you have too much of it, what ends up happening is that you will erode turbine blades, right? Think about it. It's hot water, metal, turbine blades, although I don't know if all turbine blades are metal, but there's probably some different ones. But essentially, what happens is you'll erode them, and when you erode them, the performance will drop. You'll get less power. You'll have to buy new ones. You'll have to maintain them. It increases the cost of the power plant. So the important thing is that what you're trying to do inside of this turbine stage, you're trying to limit the amount of liquid that gets in here. So what you want is this quality, as they say, at least 90%. So you want this stage never to drop below 90% because then you'll have liquid in there, right? And the way for you to do that, right, is to superheat. So for example, let me get rid of this and I'll show you the superheat chart. So if we draw a superheat, which I know that's not a great drawing, but here I'm going to draw a superheat. So, the original one that I drew was this right here. Right? Let's say this is what I drew as state 1 to 2. So this is the original one. If you draw, let's say we superheat it, right? I'm going to have to redo this part because it looks really bad. Yeah, let's do that. I'm not good at drawing this, go figure. So, if this right here is state 1 and this is state 2 of the one that we looked at previously, the saturated vapor one, to get this to have less a higher quality at the exit, if you heat it up to say superheated and then went straight down, right, you find that our quality is now closer to 1, right? And even in some cases, it ends up like this. It ends up going the opposite way. And so it ends up, since obviously in real cases the entropy is gained, it ends up being over here, which is still superheated, right? And there's no water vapor in here, or there's no water in here, no liquid. So that's the reason why you superheat it. You get more out of it, and you also avoid having turbine malfunctions due to how much liquid is in the fluid, right? And so that is a superheat. Now, a reheat is, as I said before, I will kind of draw a little diagram. Actually, I don't need to draw a diagram. It shows it down here. So this is a reheat. So essentially, if you guys recall, from the pump into here this was state 1 and 4 in the other cycle, right? It was the into the boiler, out of the boiler. This was the amount of heat being generated in the boiler, and it went straight into the turbine. But what happens is that this high pressure turbine, so that's why they break these up. This is the highest pressure in the cycle. So from 1 to 2, which is right here, 1 to 2, it expands the fluid, but it doesn't expand it all the way. It drops it to another pressure, a median pressure, as you can see on this chart. There's one pressure here, that's the highest. Then you have the lowest pressure down here, right? So it expands it to a medium pressure. And what that medium pressure is going to do then is going to run back through the turbine here, or through the boiler. And it's going to pick up that heat, right? A bunch more heat as it goes in. And then it's going to go up to state 3. Which is now higher temperature, same pressure, but higher temperature, therefore higher enthalpy value. And by doing that, between 3 and 4, which is the next stage, right? The next stage is between 3 and 4. Then it expands it all the way down to the condenser pressure, which is here, right? So straight down. And so the reason why this is good is, like I said, you'll get more out of it. You have 2 turbine stages. Also, it avoids having you to end up in here, in this liquid region, after the first turbine stage, right? It basically allows you to do it in 2 stages and avoid having a lot of liquid buildup. So these are 2 ways to combat it, I guess. And this right here is very common. Like, this is something that will be in a lot of cycles. And all cycles, and I mean all of them, are superheat cycles. I do not believe that I can't imagine there would be a cycle that is not a superheat cycle where they just do saturated vapor. I would be completely shocked if there was. So basically all of them look like the one that not the one that we did earlier, but the one that we did afterward. Let's get back down here. So that's superheat and reheat. So I'll go back down here. Like I said, basically the only difference between this one and the regular Rankine cycle, which I will draw over here, the only difference is that this one just adds another 2 states. That's it. It just adds state 6 and state 5. And it does it by simply taking out steam here and running it back through and then doing it again. And it obviously renames the states something different because you want them to go in, numerical order. So you would go, this would be 1, 2, 3, 4, 5, and 6, right? So it just goes like that. That's the only difference. You just added another turbine stage, which means that you've added another place that makes power into the cycle. So that net work equation that you get changes now. It's not the same as it was before. It is now the work generated by this part of the turbine cycle, then the work generated by this part of the turbine cycle minus the pump, right? So you do have to be careful. All right, now let's talk about supercritical. So this one is actually a little less common, is supercritical. This one, there is a plant in Illinois that does do supercritical. I think it's Prairie State. I don't know where Prairie State is located. I might find that, or someone in the chat can find it. But essentially, it says the temperature of the steam entering the turbine is restricted by metallurgical limitations imposed by materials used to fabricate the superheater, reheater, and turbine. So essentially what they're saying is that we can't go higher than, let's say, the melting temperature of the turbine, right? Or even close to it, right? Or the boiler or the reheater, because obviously if we go higher than that, or higher pressure, higher temperature, what ends up happening? Well, we have a catastrophic failure, right? And we don't want one of those. As much fun as you might think that sounds, it is not fun. So we are essentially limited by that. If we could find better materials to do this, we can raise the limit, therefore we could get more power out of it. But for right now, I'm sure they're making strides in this every day. But for right now, we are kind of these are our limits, right? These are the limits. So it says, high pressure in the steam generator also requires piping that can withstand great stresses at elevated temperatures. Still, improved materials and fabrication methods have gradually permitted significant increases in maximum allowed cycle temperature and steam generator pressure with corresponding increases in thermal efficiency that save fuel and reduce environmental impact. This progress now allows vapor power plants to operate with steam generator pressures exceeding the critical pressure of water, which is 22.1 megapascals or 3,203 psi. These plants are also known as supercritical power cycles or vapor power plants. So this right here is supercritical. Essentially what the difference is that you see this like chart here. This right here, if you guys know your calculus, is called the critical point, right? The top, right? The top where the slope is 0, right? That is the critical point. And we are surpassing that. We are going above this critical point of water. Like this. It kind of just goes like this. So up. And it doesn't even follow this curve anymore, really. It is outside of it entirely. And we'll explain that in just a second. So it says... Figure 8.8 shows a supercritical ideal reheat cycle. As indicated by process 6:1, steam generation occurs at a pressure above the critical pressure. So essentially how this works is that right here, at this line, this right here would be the, it's kind of hard to draw, but right here, this is 22.1 megapascals, right? That little dot is 22.1 megapascals. Our pressure is above that. So we are now above that pressure. And therefore we are above that temperature, right? Because if you guys recall from your saturated tables, the highest pressure you can achieve has a highest temperature you can achieve inside the saturated region. Since we are now outside of that, we can now get it way higher, right? So it says... No pronounced phase change occurs during this process, and conventional boiler is not used. Instead, water flowing through tubes is gradually heated from liquid to vapor without the bubbling associated in boiling. In such cycles, heating is provided by combustion of pulverized coal with air. It says today's supercritical vapor power plants produce steam at pressures and temperatures of 30 megapascals, that's a lot, and 600 Celsius, 1110 Fahrenheit, permitting thermal efficiencies of up to 47%. As superalloys with improved high temperature limit and corrosion resistance become commercially available, ultra supercritical plants may produce steam at 35 megapascals and 700 C, with thermal efficiencies increasing 50%. So essentially what you're getting out of this, right? So this, I know this is like a lot, but what you're getting out of this is increased efficiency. So right here, 47% is a supercritical plant now. Exceeding 50% would be with better alloys and higher corrosion-resistant materials in the turbines and everything. Subcritical, which are the ones that we are going to work with. These right here, this is just a novelty, right? We will not do any problems associated with supercritical plants. But these, essentially what the normal ones are, subcritical, like lower than the subcritical point, and they have efficiencies around 40%. So what you get is you get 7% more net work than heat going in. And 7% might not seem like a lot, but that is a massive, massive jump in efficiencies. And exceeding 55%, I mean, could you think 15% more? I mean, that's actually a massive amount. Especially in an industry such as power generation, which is like little improvements, right? Like tiny little improvements, you know? Think about it sort of like airplanes. You know, if you remove like 1,000 pounds somewhere, like you could get this much more gas mileage. Same thing with your car. Like if you remove just a little bit of weight, it could get a little far further. That's sort of what it is. You know, you get a little bit more, right, out, and that's huge jumps. And then it says, while installation costs of supercritical plants are somewhat higher per unit of power generated than subcritical plants, fuel costs of supercritical plants are considerably lower owing to increased thermal efficiency. Since less fuel is used for given power output, supercritical plants produce less carbon dioxide and other combustion gases and solid waste than subcritical plants. The evolution of supercritical power plants from subcritical counterparts provides a case study on how advances in technology enable increases in thermodynamic efficiency with accompanying fuel savings and reduced environmental impact, and all cost effectively. In the next example, the ideal Rankine cycle is modified to include a superheat and a reheat. So we are not going to do the reheat. We're just going to do a regular Rankine cycle that has efficiencies. That will be our question for today. So I'm going to go find one because you only really are going to do these reheats. Like you can see how these get a little more complicated. Although you'll never have to do a question like this. I did these in Thermo 500 where we actually had 3 of them. It broke out here, broke out here, broke out to another one, and then it finally went down into it. But you do it on a computer, so it makes it a little easier, I guess. Let's go and find these. Here we go. Here we go. This is a good one. So I'm going to snippet this, and we're going to open up Paint, and we're going to do it live. Okay, this is good. I was making sure the question wasn't too difficult. But it's fine. This is right here is what you would call a very typical question for this type of problem. So very typical. So let us begin. I'm gonna need your inputs here in a second. So it says, steam enters the turbine of a Rankine cycle at 16 megapascals. So I'm going to go ahead and first thing I'm going to do is I'm going to draw the TS diagram. Maybe. See if I can get this working. Right, so TS diagram. So, this might be another bad drawing, but, you know. So, this is our TS diagram. That'll be the first thing we'll work on as we move through this question. So, the next thing is, let's go ahead and do the givens. Everything we know about the question, same as usual, right? So, given. So, it says, steam enters the turbine of a Rankine cycle at 16 megapascals. So, we have steam. And pressure 1. So it says it enters the turbine of a Rankine cycle. So pressure 1 is going to be 16 MPa. You can name these however you want. Like you could have this one be 4, it could be 3. It doesn't matter. But generally speaking, the book does leaving the boiler, entering the turbine as state 1. Other books do it differently, but we're just going to do that one. That's how we're going to hold on to it. So pressure 1 is 16 megapascals, and it says temperature 1 is 560 C. So those are the first two things given to us. And then it says the condenser pressure is 8 kilopascals. So let's look at that. So this would be P2, which is also equal to P3, which is equal to 8 kPa. Right? And then it says the turbine and pump each have isentropic efficiency, so A to T and A to P of 85%. And then the last one is the mass flow rate, so M is equal to 120 kilograms a second. And it says what we are trying to find net power developed, so work net, heat transfer to the steam passing through the boiler, so this would be Qn, and the thermal efficiency, so eta therm, is what we are trying to find for this question. These are all the things we were given. This is what we are trying to find. Although I didn't get eta therm down there, I will add that in just a second. So these are what we're finding. But first, obviously, we need to find everything else associated with it. So let's start with state 1 as usual. So state 1. So state 1, this is going into, so let's go back to this really fast. Come on. I hate when I do that. I'm going to get us a diagram. So this right here is the diagram. Now obviously these numbers aren't going to be hours, but I'm going to go ahead and take this into the other thing so you guys can see where we're at. Come on, no. We don't want that. So this is our diagram of the question. So it says that state 1 going into the turbine, right? We can clearly see that. Now obviously the mass flow rate is not 12. I'll get rid of that. But everything else is correct. So we need to find all the numbers associated with these states, right? That's our first step. So let's do that. So we need to find H1 and S1, right? H1 and S1. So we got to go to the tables. So we were given pressure 1 as 16 megapascals, and we were also given temperature 1 as 560, if I recall. Yes, so 16 megapascals, so pressure 1 is 16 MPa, T1 is 560 C. So what we're going to do is we're going to go to the tables, and we're going to go look this up. Now we need to find out where it is. Is it superheated? Is it saturated? I'm going to tell you it's probably superheated, but we will see. So 16 megapascals, which I believe is 160 bar. Is our temperature greater than this? It is. We're at 560. The saturation point is 347, which means that we are way above, right? We are superheated to the max. So we must go once again and find 16 megapascals in here somewhere. Right here. So we're at pressure, in the superheated tables that is, pressure of 160 bar or 16 megapascals. And we need to go and slide across and find 560. So 560 is on that line right here. And we need to take that value and this value for ours, right? These are H1 and S1 respectively, the enthalpy at state 1 and the entropy at state 1. So let's go ahead and write those down. So we have 3465.4 to 3465.4, and this is kilojoules per kilogram. And then we have S1, which I did not remember, is 6.5132. So 6.5132, and this will be in kilojoules per kilogram Kelvin. right? So this is state 1. It has been solved. Now what we're going to do is we're also going to put this on our TS diagram. So this doesn't have to be drawn to any sort of scale. You're just using this as a reference to how you're going to do the question. So let me go ahead and I'm going to do this in a better way. Let's do that. I was going to try and hand draw that, but I feel like it was going to be bad. So this right here is our pressure line. This is our first pressure. So this is P1, but it's also pressure 4 because pressure 4 is on the same pressure line as state 1. So it's P1 or P4. So I'm just going to draw us right here. You know, it doesn't, like I said, there's no way of really scaling this properly, but I'm going to draw us right here. So we are on that line right there. And this will be state 1. Pretty straightforward. We are in the superheated region, and I drew us on this line. It's kind of like it's kind of arbitrary, anywhere you draw it. But we are state 1 right there. Now, to solve for state 2, this right here is how you'd solve basically all of them, unless they give you something about state 2, like a temperature. But we are going to solve state 2 by assuming that it is assuming isentropic. So I'm going to move us straight down here, like that. We're going to assume isentropic behavior for this state. Now, you guys are probably wondering, you're like, well, wait a minute. How is this isentropic, right? Because they gave us enthalpies, or they gave us isentropic efficiencies. You are correct. We have isentropic efficiencies, but those are efficiencies of the turbine that we are going to deal with in just a second. So this right here is the pressure line of P3 and P2. And this right here is going to be state what? Well, this one is going to be 2S because it is the isentropic state of 2, the perfect state, right? So 1 to 2S. And how we solve from 1 to 2S is very straightforward. We just assume that entropy 1 equals entropy 2, right? So let's go ahead and do that. So state 2S. You are going to say S1 equals S2S, and that equals 6.5132 kilojoules per kilogram, right? Kelvin. And you are also going to know that pressure 2 is then equal to 8 kilopascals. And knowing these two things, you are then able to go into the tables and you are going to go find if we are superheated, are we in the saturated region. My chart ended up showing we are in the saturated region, but that's not necessarily true. This could have been higher superheated. It ended up over here. We don't know yet, and I'll redraw it if we end up being wrong. So let me go look. So we are looking for 8 kilopascals, which 8 kilopascals is this right here. It is 0.08 bar. And we are looking for if our entropy ends up in this area. Is our entropy between these two values? The answer is yes, because we are 5.3 something. And it is bigger than this, but less than this. So therefore, we are in the saturated region. So our diagram so far is correct. We are in the saturated region somewhere. Now we need to figure out how far into the saturated region. So to do that, we need to do X2S. We need to find the quality. The quality, simply, how much vapor, how much liquid we have. So how we do that is we're going to use our entropy value. And our entropy value is 6.51, not 51. So, pardon me, I said that earlier incorrectly. So we're going to do the quality equation, which is the entropy. I'll write it out in long form. So S2 minus SF at the pressure divided by SG minus SF at that same pressure. So this right here, and this is at 8 kilopascals. So 6.5132 minus SF, which was 0.5 something, 0.5926. Nope. And then we have to do the big one, which is 8.2287. And also minus 0.5926. And like I said, this is how we get the quality. And this answer is going to be equal to, once I get my calculator out, that's why I need someone in here to be my calculator. Preferably someone who's not driving. And it looks like it's going to come out to be 0.77. So 77.5, let's call it that. So our quality is 77.5%. So far our graph looks okay. But like I said, it's arbitrary. It can, just as long as it kind of matches the zones. If you want to be accurate, it just has to match which zone we're in. Are we in superheated, subcooled, saturated, right? And now that we know this, we now have to find H2S, which is the enthalpy corresponding to the isentropic state, which would be HF plus X2S times HFG, or Hg minus HF. And if we do that, we end up with, I think this one's the 191, or 170. Let me see. Yeah, it's 173.88. I was right. 3.88 plus 0.775 times, and I'm going to use their value for FG, which is 2403.1. And that means our enthalpy value is going to be 2037. So 2037.11. So this right here is, let me get that over there. So this is state 2S. So we have solved state 2S. We found our enthalpy. Hooray. Now we have to solve the actual state, because very clearly if our turbine has an efficiency, it means that it's not isentropic. It means that there is some losses happening. And so for us to solve the actual value of state 2, we have to use that efficiency. So let's go up here and do state 2. So state 2, the actual state, if they give you an efficiency, they want you to use the turbine efficiency equation, which is A to T is equal to H1 minus H2S, and divided by, not H2S, apologize. H2 divided by H1 minus H2S. So essentially what this is the work of the turbine, the actual turbine, divided by the work of the perfect turbine. And this is some efficiency, and for us it's equal to 85%. So I'm going to write it out in the form now, which is H1, which is, what did we get for H1? 3465.4 minus H2, which we do not have, which is what we're trying to find. And then 3465.4 minus H2S, which was 2037.11. So this is our equation. And if you maneuver this equation and you solve for the unknown value, which is that right there, you will find the final equation to be this. And I just memorize these eventually, because it comes up a lot. So it's H1 minus A to T, which is 0.85 times H1 minus H2S. So if you want the equation, this is where, if you maneuver it, this is what you end up getting. You get H2 is equal to H1 minus 0.85, which is your A to T value, times H1 minus H2S. And if you do this, which I will do in just a second, you will get H1, which is 3465.4 minus 0.85 times 3465.4, 2037.11. You get 2251. So I will put that out here. 2251.35. And this is kilojoules per kilogram. And this answer makes sense. And the reason why it makes sense is because the higher the enthalpy difference between the turbine and the entry and the exit, the more work it did. This right here is closer to that value than this is to that value, which means that we made less work. And it makes sense because it was an efficiency. We lost something, right? So that means our work went down because it has an efficiency. It's not perfect. And so this makes sense as an answer. So now, since we have done state 2, we get on to the easiest one of the cycle, which is state 3. State 3 has always been the easiest one. It's always been my saving grace, because you can always get points for state 3. So, state 3. So, state 3 is after the condenser. But before I do that, I'm going to actually draw this part. So, here's the thing, is that we don't know where H2 is, so I can't really draw it on the graph, but I can show you how I can figure it out. So if you go here to the saturated tables, you'll find that our enthalpy is still between these two values. Pardon me. It's between these two values, 173 and 2577, which means that our value is still inside the saturated region. We are not superheated even after that state. So this is going to get really difficult for me, so apologies in advance. It's like over here somewhere. So this is state 2. It's further to the right than state 2s was because we gained entropy, but it goes down in sort of like an arc. I can't draw it very effectively, but that's how it is. It's because it's not to scale, obviously. If this were to scale, they'd be further apart, but hard knowing. All right. So we are there. Now we are at the condenser. So we are past the condenser, actually. So state 3. So if you go over here to state 3 is after the condenser. And the job of the condenser is to lose all of the heat, right? We're trying to throw all the heat out of the cycle to get it to go through the pump because we want this to be a liquid pump. We want it to have no vapor or gas in there, no vapor, right? So we want all liquid, so therefore the job of the condenser is to make it to where it gets to the pump at all liquid. So we are going to assume that all liquid is going into the pump, which is x3 is equal to 0. And we also know that pressure 3 is equal to pressure 2, which was equal to 8 kPa, right? So knowing these two things, you can go right to the tables and you can go, okay, well, we are at 8 kilopascals, and we know that it is saturated liquid, right? Quality of 0. So that is our value for our enthalpy. Also, at this turn, we want to make sure that we grab the saturated liquid value for a specific volume. And that is because we need to use that to solve through the pump. So let's hold both of these. So we want 173.88 for enthalpy 3. And then we want V3 is equal to 10084. But remember, this is times 10 to the third. So it is 0.0010084. And this is in meters cubed per kilogram. So this is state 3, and it has been solved fairly easily. State 3 is always the easiest one. Now we have to solve the next state. So I'm going to go ahead and draw where we're at. We want this one. So let's draw where we're at. So we are way over here now. So we went from where we were at 2 and 2s to all the way to a quality of 0, which is right here. So this is state 3. State 3 is at this juncture right here because we know we're all saturated liquid. Now we're going to do the same thing we did with the turbine except with the pump. So we are going to assume isentropic behavior. So 3 goes to 4s, right? And then somewhere over here will be state 4, which I'll kind of draw it already. So we have 4s and 4. So first we have to solve for s. So as I did the other day, the perfect pump equation, this is how you solve this one. So the perfect pump equation, if you guys recall, I will go ahead and write this out. I'll put it, yeah, we'll do here. So this will be state for S. So the perfect pump equation is equal to this. So we have the work of the pump, which is equal to H 4S minus H4, or H3, which is equal to V3 times the change in pressure, which is P4 minus P3. So if you wanted to solve for H4S, like right here, you would move H3 to the other side, and you end up with the following. You end up with H4S is equal to H3 plus V3 times P4 minus P3. And that is the perfect pump equation. If you want to remember this, remember it. And once you do this, you will end up with the following. So H4S is equal to 173.88 plus 0.001084 times, and remember what I told you, you want this in kilopascals to get it to work out immediately. Unless you want to just multiply in by factors, you could do that, but the kilopascals way has always worked for me. So we want 16, since it's 16 megapascals, that is 16,000 kilopascals, and we have 8 kilopascals, so it's 16,000 minus 8. And by getting this number, you will get the following as an answer. So 173.88 plus 0.001084 times 16,000 minus 8. And you get 190, pretty much on the dot. So I'm going to just call it 190.01. This is kilojoules per kilogram. So that is state 4S. I'll go move this way. And now we have the actual state 4, and we solve this one the exact same as we did the turbine. So we know that the efficiency of the pump is equal to H4S. So remember, for a pump and a compressor, they flip. The perfect one is on the top now, and the not perfect one is on the bottom. So the isentropic state's on the top now, and I'll explain why in just a second. Minus H3. So this is the equation for the isentropic efficiency of a pump, and the reason why they flip is because you want this to be a percent, and the percent has to be, so this right here has to be the highest, right? Because if the highest one was on the top, it would be over 1. So the highest one for a pump is going to be the one that was least efficient, because our pump required more work when there was an efficiency taken into account. When it was perfect, it required the least amount of work. It was the best it would ever do, so we didn't have to put in as much into it. So that is why the isentropic is at the top. Now, knowing that, we can continue and write this out. So we have 190.01 minus H3, which is 173.88. And then you are dividing by H4 minus 173.88. So this right here is our equation. And what you will get when you solve this, once again, if you want to remember this, you are more than welcome to. You will get H4 is equal to H3 plus H4S minus H3. And you will be dividing that part by the efficiency of the pump, which is, in our case, 0.85. So it's just this. It's this plus this right here. And if you do this, you will get 173.88 plus 190.01 minus 173.88 divided by 0.85. I got 192, so 192.86 is our answer. So we have now solved every state point in the question, right? We have state 1, 2S, 2, 4S, 4, and 3. All of them are completed. Now we have to do the actual question, right? I know this might seem like a lot, but once you get into the hang of it, it really isn't very much. Like, you can solve these very fast once you get good at them. Like, if you know what to do at every step, just like that, it'll flow really quickly. So now let's solve up here. So this will be the solution window. So solution. So the first thing we wanted to find was the work net, right? So we are looking for the work net in kilowatts. So if you guys recall, the work net is equal to the work of the turbine minus the work of the pump, right? And if you do this in terms of enthalpies, you will end up with the following. You end up with mass flow rate, which we have, times H1 minus H2 minus H4 minus H3. Let me move this over. H4 minus H3. This right here is the work net of our question. So our work net, when you do this all together, you will end up with the following. And the reason why it's 1 and 2 is because this is the work of the turbine. It's just the state points surrounding our turbine, which was 1 and 2, the enthalpy difference. And the pump is 3 and 4 because that's also surrounding it, right? So the work net of this question, which I will get in just a second. So we have H1 minus H2 is 3465.4 minus 22 something, 2251. Make sure you use the actual ones, not the isentropic values here. A lot of people make that mistake and they lose just a little bit of points. Not a whole lot, but they end up losing something, and you want to try and hold on to those in a death grip. And so you multiply by 120 and you end up with the following. You end up with 143,408 kilowatts, something like that. So you end up with this as your kilowatts, and you could obviously put this into megawatts, but you get the point, right? So we have 143,408, and now all I did was I took this quantity, subtracted off this quantity, and I multiplied it all by the mass flow rate that we have in the question, which is 120, and you get that as your answer. Now let's move down to Qn. So Qn is just the amount of heat that we had to put into this cycle, right? So I don't know why they're showing these. I guess these aren't supposed to be here. These 5 and 6, supposed to be 1, 2, 3, and 4. But anyway, it's just this. It's the enthalpy difference going into the steam generator. You can even see Qn right here. So this is heat going in, right? And so for heat going in, it's just the enthalpy difference, like I said. So the enthalpy difference is just like this, M. And they said they want it in kilowatts, so this is good. You're multiplying by mass flow rate. You want H1 minus H4. And if you do this, you end up with, typed it all in using all your enthalpies, 3465.4 minus 192.86. 120. You end up with this 392,704.8, and this is kilowatts again. And so that is the amount of heat that it took. So just to show you, that's the amount of heat it took to get the fluid from a subcooled, which is way over here, all the way back up to here. Essentially, that's how much heat we had to put in, right? In kilowatts to get it back up to here. So now we have the last one, which is the thermal efficiency. So the thermal efficiency, very straightforward, which is eta therm. And this is what we want in the cycle divided by what we had to put in. So want over input, right? And since this is a power cycle, what we want is work net, right? We want the work net. We want the power going out to the houses to power your iPhone chargers or whatever, right? So work net, and what we had to put in, well, we had to put in the heat transfer, right? This is what we had to put into the cycle to power it. This is the amount of energy we put in, the highest amount of energy we put in the cycle, which is Qn. And so if you do this, you end up with taking our work net up here, which I'm going to put it into long form equation because this is for a Rankine cycle. This is what it looks like. I will put the long form. So this is what it looks like, but obviously since we've already done these two, you get an actual answer right off the bat. because we were asked to do them. In the previous part, we found WorkNet and QN, so you will find that adatherm, when you put those over each other, which is 143,408 divided by 392,704.8, you end up getting 36 or 0.365. So essentially, yeah, it's about right. So it's 0.365, which is about 36.5% efficient. So that is our solution to the question. So let me go ahead and do that. So these are the answers to the question. So this is a very typical question for thermodynamics 2. You will get a question like this at the very beginning, and not only that, you will be required to do these exact processes like this for cycles that contain the reheat, cycles that contain regenerative qualities, which are like open feed water heaters and closed feed water heaters. But if you get this process down right here, this S1, S2, find the actual S2 or the actual enthalpy, you move along like this. This is the process for every question in this class. It's very repetitive, but if you can drill it down into your head, this is how you solve all of them. And I promise you, if you can get it down, you will do very well in Thermo 2. Probably even better than Thermo 1, because Thermo 2, this process does not really change. Now you'll do it with air, right? Like air might be the fluid, and you'll use those PR values we mentioned very, very briefly, like PRs. But it's the exact same process for basically every question. So, especially chapters 8 and 10 are basically the exact same process of what I've just listed here. Chapter 9 is a little different because you're using the air tables because of gas. But besides that, so basically out of the chapters you guys do 8, 9, and 10. So 8, 9, 10, and 13. Out of those chapters, 2 of them are exactly the same. One of them is very similar, and combustion is completely different. No help there, unfortunately. But that's how the show goes. But if there are no questions, we're going to end this, and you guys will be free to go. But I will take attendance before you go.